Okay, let's go through your test paper on differentiation. So it consisted of 5 questions and 36 marks. Talking through the questions, question 1 was an IB question. Question 2 was an IB question, I think. Question 3 was not, but that's fairly standard in terms of what you're getting. Question 4 was also not. And then question 5 was more testing our knowledge. So I'd call that more of a textbook question, filling in the boxes on that paper. So let's look at the first question. I think this was a really, hard question for an IB paper. And facing that in the IB, it's interesting, but I'm not sure I want to be there. The real thing here to focus on is think about all your definitions that you know. So I released a video last week on the definitions of increasing, decreasing, inflection points, maximum and minimum. This is really putting that all into practice. So the most important thing to notice in this question is that this is the function of f dashed, so of f dashed of x, which is the same as our differential. And so you can think about that as your gradient function. So that's what I bear in mind when we're looking at this graph. So obviously it's increasing all the way through, and then it reaches this sort of maximum point, decreasing, minimum point, maximum point, minimum point. Let's look at the question asked, therefore. The graph of f dashed, the derivative of f, okay, that's the important part. Let's highlight some stuff. The derivative of f, so it's f dashed, which is the derivative of f, has intercepts at x equals p, 0, and t. There are local maximum points at x equals q and t, and local minimum points at x equals r. Well, that doesn't really tell us anything more than what the graph was saying. Find all the values of x where f is increasing. Well, I'm not even going to look at the graph for now. I'm just going to write down the definition. Increasing. What does increasing mean? Increasing means that f dashed of x, or our dy by dx, is greater than 0. So we need our function to be greater than 0. So let's look at this. At what points is it greater than 0? Obviously greater than 0 all the way here. Then it's less than 0. There's no other point where it's greater than 0. So for part A, we need all the part there that I've highlighted in red. So we need x to be between 0 and p. Great. Part B. Find the value of x for which the graph of f has a local maximum. Well, let's think about what local maximum would mean. So a local maximum means that our differential, f dashed of x, or dy by dx, will be equal to 0. That's a stationary point. So that implies that it's a stationary point. What do we need to know if it's a local maximum? A local maximum would mean that our second differential of x, or our d squared y over dx squared, would be less than 0. Now that's a key part to note. Why would it be less than 0? Because if we're thinking about a local maximum, we're going up like this and down like that. So our gradient is going from, let's say, 2 to 0 to minus 2. So the whole way across here, it's decreasing. And because our gradient is decreasing, our change in gradient is decreasing. So let's put this as a side note somewhere. Because our whole gradient is decreasing, what we really want is our second differential, second order differential, to be like this, less than 0. Which is interesting. Maximum point means your second order differential is less than 0, minimum point is greater than 0. So that there would imply that it is a maximum point. Okay, so we need a point where the graph equals 0. Well, there's only a couple of points where the graph equals 0. Let's highlight those in purple. Equals 0 there, and equals 0 there, and equals 0 there, 0 there. And then we need a point where the second order differential is less than 0. So that means that the gradient function is decreasing. So in fact, the only line here where it's decreasing is there. No other point there where it's decreasing, because we need the change in our gradient. So this is our gradient function. We need the gradient of the gradient function to be less than 0, if that makes sense. So the gradient of the gradient function less than 0, and that's the only one. All of these other ones here, that's bigger than 0. It's positive. You know, let's say that's 5 or something. This could be -1, and then that's 0. So the only one that fits here, let's double underline our answers, is x is equal to 0. That's it. Okay, because of those definitions there. Part C, part I. So find the value of x where the graph f has a local minimum. Okay, well, let's look at our definitions. We just did it for the previous question. So we need the first order differential, dy by dx, to be equal to 0. And we need our second order differential, so the change in our gradient function, I'm going mad, dy squared, d squared y over dx squared. And we need that to be, this time, greater than 0 for our minimum points. So note that this here was less than 0. The other one here is greater than 0. So let's think about that. So we need 0, so it's either one of those purple points, but this time we don't need this line, we need it to be greater than 0, so again we can't take that one because it's equal to 0, it's an inflection point. So we need this one here, so we need x equal to p. So x equals p. X equals p. Let's double underline that. P is obviously negative here. Okay, and the second part here, this is almost the easy one. Inflection points. So inflection point means that we have the second order differential equal to 0, and that implies an inflection point. So the only one where the second order differential would be equal to 0, where the change in the gradient is 0, actually it could be here, either at Q or at T, because both of those points there, you see the gradient of the gradient function would be 0. So it could be here, that's what I'm saying, or it could be here. So we'll write down both. X is equal to Q, I can't do my Q's, or T. So either one of those is fine. And that's a question done. Always remember to double underline your answers. Okay, that took up just over 10 minutes, which is kind of crazy. But that's a real sort of, grade 7 question that you'd be facing, for those extra couple of percent that would guarantee you to get over 70 for your grade 7. Okay, let f of x is much more standard equal ln of 5 of x. Show that the differential is that. Fine. So I gave you the formula there as well, but that's also in your formula booklet. So in this case here, let's just write down u obviously is our ln of 5x, and v is our k of x. So let's differentiate these. U dashed, well, we've learnt the formula for this. If we've got a ln of f of x, let's write down our formulas in... if we got a u in orange, ln of f of x, we've learnt that the differential u dashed would be f dashed of x over f of x. And so therefore u dashed here would be f dashed of x, so 5 of x differentiated is 5 over f of x, which is 5x. Well, that's just 1 over x. And if we think about that, that makes a lot of sense, because on a side note here, ln of 5x is equal to ln of 5 plus ln of x, by our rule 1 on our logarithms. And so therefore, when you differentiate, this here is just a constant, and so it would just be eliminated anyway, so you'd be left with 1 over x, plus 0 for your differential, if we thought about that. And so that actually turned up again in this paper. So it's an important one to know. But I think the more practice you do on this, the easier it'll be to see that, and you'll make life a lot easier. So if we take the other one, this is the more standard one. The only thing here that we've got to notice that k is a constant. That's what they try to mention here. K is of reals, positive real numbers. So we don't have to worry about anything really there. We can just treat it like a constant. So this is just our basic formula. If v equals x to the power of n, then our differential v dashed is just n x to the power of n minus 1. I'm just writing out the formulas as our first test on this so that we get used to it. And so therefore our differential here, if we take away 1 from the power of 1, minus 1 is 0. Multiply it first, we just left with k. Okay, so let's put that all in together in our formula. So we know the differential of f of x, therefore. F dashed of x is u dashed v minus v dashed u over v squared. Okay, u dashed was 1 over x times by v. V is k of x. And then we've got v dashed. Well, v dashed would be k, and u is ln of 5x. And so putting that all over v squared, we would get this over kx squared. I actually think the most difficult part of this question now really is this simplification. I think 3 marks is rather stingy, let's put it that way. I think they definitely could have increased that to 4. I just think these next few steps are what makes this question hard, but they're probably only worth 1 mark or so, which is kind of annoying. But if you want it, you've got to do the work. So let's think of some clear cancellations we can make. I can see one very clear one here. Let's just cross out those x's, because we're dividing by x and then we're multiplying by x, so all we're left with is k there. And let's just start off with this then, rewriting it like that, and then over kx, let's do k squared, x squared. Another clear cancellation that comes in here that we can see is that there's k's on the top, but actually I'm going to bracket those out just so we don't make a mistake there. And that's something key, because if you were to cancel out your k here, the danger is that you then make this 0, but in fact it's 1, because all you're doing is dividing through by k. So easiest to eliminate that danger and just factor out what you want to cancel from there. Okay, let's try to do 1 cancellation per line or something. Over k, and then I do kk x squared. And that makes it very clear that when we cancel, let's cancel the other way actually, we're just left with that function, which is what they want in the question. So we're left with 1 minus ln of 5x over kx squared. And so at university what I used to do is I would do a little box here and I'd say, proven as given in the question. You don't really need to do that, but some sort of indication that you're done with your proof and that you've shown it formally is a good idea. So this is part A, long part A. Part B, find the x-coordinate of P. So the differential has exactly 1 maximum point P. So this is our differential. And so this question I actually really didn't like, and I'll show you why. Because if we have our differential f dashed of x, and then, well, of course, to find our stationary points, we need it equal to 0. So this here finds our stationary points, 1 minus ln of 5x over kx squared. The reason I didn't like this is because there's no intention here that you've got to find your second order differential. Technically, ln of 5x equal to a constant is going to have 1 solution, but it would have been nice to sort of differentiate it to the second order first and then put that all together. But I do understand what they've done here as well, because then you could have shown, well, if it's a maximum point, the second order differential has to be less than 0. Okie dokie. So if you're setting it equal to 0, you can immediately just multiply through by kx squared, and you've cancelled that out. And so what we're left with is 1 minus ln of 5x equal to 0. Solving this, ln of 5x is equal to 1. And so therefore, I always think of log 10 over 100 equals 2. It's the most obvious case. And therefore, you don't really ever get mixed up on the order, but that's just one man's opinion. I don't think anybody ever told me to do that. I just sort of wrote that down on every logarithms question that I did. But this implies that if we think about it, we've got ln, or which is log base e, and so therefore 10 squared equals 100, so e to the power of 1 equals 5x. And so therefore x is e over 5. Okay, part C. Again, underlining the answers. Part C, show that the x-coordinate is that, if we do our second derivative, has exactly one inflection point, but that's handy to know. You could have said it as one stationary point in the question below, but I won't blame you. So let's do the second order differential. So if we take this function here and duplicate that, pull it down, f of f dashed of x, well, we'll differentiate that exactly the same way as we did before with u's and v's. So if I set my u equal to 1 minus ln of 5x, and my v equal to kx squared, well then u dashed would be minus 1 over x, because we know that ln of 5x, we did that previously, just differentiates to 1 over x, so we've got a negative of that. And our differential here would be multiplying by 2, taking 1 away from the power, 2kx. Plugging this all in, our second order differential of x would be u dashed v, so minus 1 over x times v kx squared. Minus, did I do minus here? I should have done a minus. Yes, I did. Minus v dashed, so 2kx. And then u, 1 minus ln of 5x. I like doing lots of brackets. You can even do brackets around all of this. It's absolutely fine as well. Over v squared, so kx squared, and then squared. Keep your brackets in, makes life clearer. And so therefore, let's do some of our obvious cancellations. Again, I can only really see one at the moment, so let's do that one. So what we're left with here is minus k minus 2kx plus 2kx ln 5x. Okay. And then this is k squared x to the power of 4. And what do they want it to simplify to? Show that the derivative simplifies to that. Okay. Let's think of some other clear ones that we can do here. Well, we can factor out k and x from the top line. So we get kx factored out from the top line, then we get minus 1 here instead of that term. Minus 2, well, this is obviously minus 3. Let's just write minus 3. 3 lots of that. And then we've got plus 2 lots of ln 5x over kx. I'm going to use brackets here, you really don't need to, but kx to the power of 3. So we've got kx top and bottom. Let's cross those out. Let's see if we've got what they want. Looks like we have. I'm going to add another page here. And so therefore this simplifies down to what we have in the question, which is 2 ln 5x minus 3 over kx cubed. Bingo. Okay. Inflection point. So that means we need all of that equal to, we need f dashed of x, double dashed of x, equal to 0. And so we need 2 ln 5x minus 3 over kx cubed equal to 0. So again, we can just cross out the bottom bit, we don't need it, because if we're multiplying through by kx cubed, we're going to take out that solution anyway, and we can't have that equal to 0 because we get something like infinity. It has to be constant greater than 0, or not equal to 0, basically. And so therefore we can cancel it just like any other constant in a way. We're dividing by here because we've got 0 on the other side. So if we've got 2 ln of 5x equal to 3 left over, so 3 over 2 equals ln of 5x. Log 10 of 100 equals 2. I won't write it out again, but that means that e to the 3 over 2 would equal my 5x. And so therefore, x is equal to 1 over 5 e over 3 over 2. Is this another show that? Oh, they didn't even ask us to do the second order differential. Oh, well, we did anyway. Okay, show that that equals that. Bingo, we've done it. 3 lines through it. Finito. Okay, question 3. So question 3, let's label this as y. We've got 2 plus 3x squared e to the 2x, pretty standard. Our differential dy by dx is going to be u dashed, which is this first part, differentiated 6x. V is e to the 2x, stays the same, plus v dashed, well, v dashed is our 2e to the 2x, u, which is 2 plus 3x squared. Doesn't say simplify it, doesn't say any of that, leave it like that, absolutely fine. Part A done, 3 marks, fairly generous, easy peasy. Okay, part B, show that it's increasing for all values of x. This is more difficult. So that means that we need our differential of x greater than 0. That gives you a mark straight away. You know what increasing means? You've set it greater than 0, the differential, which means our gradient's increasing, so that would make sense. Sorry, our function's increasing because our gradient's greater than 0. If our gradient were increasing, we need our second order differential to be greater than 0 because it's the change of the change. So, okay, let's play around with this. So that means that we need 6x e to the 2x plus 2e to the 2x, 2 plus 3x squared greater than 0. Let's actually multiply this out on this line, just to save some space. So 4e to the 2x, and then the other term we're going to get here is 6 x squared e to the 2x. So we can factor out e to the 2x here, e to the 2x, and then what we're left with on the inside of the bracket is 6x squared. In fact, we can factorize out 2 as well here. So we're left with 3x squared plus 3x plus 2. And we now need that to be greater than 0. Okay, well, let's treat these individually. So if I just look at this here, that's always going to be positive. It's always going to be positive because e to the 2x cannot be negative because e is a positive number. We know the value of that. So this here is always positive. Let's think about our other term here. So all we're left to prove is that this here is greater than 0. Well, how do we show that? One way of doing it is completing the square. That's probably the easiest way to think about it. The other way to do it would be to find your minimum point, show that it has a minimum point basically, and then it's like this above the x-axis, if we imagine our x-axis like that. That's basically what we want to imply, because that means that all values of y are positive. If that makes sense? So let's try show that with both ways. So I'm going to first do method 1. So if I do method 1 here, let's say we're going to try and complete the square here. Well, to complete the square, we got our 3's in here. Let's take our 3 outside. 3x squared plus x plus 2 over 3 is greater than 0. And so therefore, well, we don't really need to worry about our 3 at this stage. If we show the inside bit's greater than or equal to 0, then we're okay. So I'm just going to eliminate that, get rid of it. Okay. So let's complete the square with the inside here. No, I want to keep that there. So complete the square with the inside bit here. We need half the middle term, so we need half of this 1 here. So we need x plus a half squared minus that half squared plus 2 over 3. And we want to show that's greater than 0. So that means we've got x plus 1 over 2 squared, and then minus a quarter plus 2 over 3 greater than 0. And so that means we've got x plus half squared. Common denominator, sorry, is 12, so therefore multiply the first one by 3, second one by 4. So we've got 3 minus plus 8. So therefore we're left with plus 5 over 12. Greater than 0. Well, this is another way actually. I'm going to just write down. Let's go shorthand for positive. Well, this here is obviously positive, and this is obviously positive. That's one way of doing it. Both terms are positive. Squared terms always going to be positive, and then you've got a positive constant. The other method, which, I don't know, I might have leaned towards, although it's more long-winded, is to take your function y equals 3x squared plus 3x plus 2, and then try to visually show, as I was saying, that this here is above the x-axis. So we can try that. Our differential, dy by dx, would be 6x plus 3. Okay, so if we set that equal to 0, we would get the solution x equals minus a half. Let's do our second order differential, d squared y over dx squared equals, we don't even need to do that second part there, d squared y over dx squared, and the reason being is because it's only going to have 1, and that's what we see when we double differentiate. We're just left with 6, which is greater than 0. That means it has a minimum point, and the minimum point is, have I shown it's above the axes? No, I haven't. So maybe in this case you do want to find your x and just show that it's above the axes. So we know it has a minimum point, we just don't know whether it's, looking at our graph here, we don't know whether it's like this or whether it's like that, basically. And so we're trying to find that it's above our x-axis. So we do need our x solution here, x equals minus a half. Let's plug that in to find our y solution. So that means that our y solution would be 3 lots of minus a half squared plus 3 lots of minus a half plus 2. Well, minus a half squared is a quarter, so 3 over 4 minus 3 over 2, so that's minus 6 over 2. 6 over 4, sorry. So 3 over 4 minus 6 over 4 gets you to minus 3 over 4 plus 2. So 2 minus 3 over 4 would get you to 5 over 4, which is greater than 0. So, so therefore we've shown that it is above the line. And if you wanted to do this method and you have time, I'd always do a quick sketch. It just shows to the examiner this person really knows what they're talking about. So that's our 5 over 4. Pretty terrible diagram, but it doesn't really matter. Oh, I'd want to do it. No, I do want to do it the other way around. So imagine we're like that, x, y. This is called a sketch because there's very little accuracy in it. And then we're at 5 over 4. And even though that doesn't look like negative a half, we'll just keep it like that. And so therefore, you know, it's obviously greater than, or it's positive. Okay, done, solved. Question 4. We've got y equals ln of a third x coordinate of p is 3. Find equation for the normal curve. I've got 8 minutes left to do 2 questions. Boy, before we get stampeded by my3s. Okay, x coordinate of p is that. Find the equation to normal curve. So if we've got y equals ln of a third x, our differential, dy by dx, would be the differential of the inside of the bracket over the inside of the bracket, which is just 1 over x. We've done this prior to this. So at 3, the differential at 3, our gradient would be 1 over 3, implying the normal would be negative 3. And so therefore we can plug this all into our y minus y1 equals m lot of x minus x1. So we haven't quite figured out what y1 is yet, so let's put in at x equals 3, we'd have ln of a third of 3, which is ln of 1, which is 0. Let's make some more space. This is my honest decision. Ln of a third, let's put this in like that, at x equals 3. And then we differentiated it, and so we have all our parts here. So this here is our y1, this is our m, and our x1 is obviously 3x1. So y minus 0 equals minus 3x minus 3, so therefore we get y equals minus 3x plus 9. Done. How many marks was that worth? 5. Okay. 2 minutes for 5 marks. Do that. 6 minutes for 7 marks. Increasing intervals. Okay, well I'm just going to quickly write down. Increasing means dy by dx is greater than, they've just used f of x, so we'll just do f dashed greater than 0, f dashed less than 0. No, I've just got to quickly record a solutions video. Yeah. Yeah, chat later. Maximum points and minimum values. So maximum point and minimum values. Maximum point means our differential is equal to 0 and our second order differential is less than 0. Minimum point means our differential is equal to 0 and our second order differential is greater than 0. Inflection points means that our second order differential is equal to 0, and then concave up and concave down, we can kind of imply those from those ones. So if we're given a function here, f of x equals x to the power of 4 minus 8x squared plus 5. Let's find all the different parts here. F dashed of x would be 4x cubed minus 16x. We need that to be greater than 0, so we kind of need to find our critical values. So critical values is when the differential is equal to 0. So let's find those. So if we've got f dashed of x equal to 0 equal to 4 x cubed minus 16x, take x outside, get rid of the 4. What we're left with is 0 equals x outside of x squared minus 4. Well, that's x minus 2, x plus 2. So our critical values are going to be x is equal to 0, minus 2, 2. Probably should have done minus 2, 2, 0 and 2. Okay, so let's draw our line here. We've got 0 to minus 2. Let's think about our bits in between. So let's try 1. Let's try this one at 1. See what we get. If we put in 1, f dashed of 1 would be less than 0. And so we could also try another one just to double check that we're not making any mistakes, but I'm going to assume here for sake of time greater than 0, so f dashed of x is greater than 0, f dashed of x is less than 0, f dashed of x is greater than 0. So therefore we've got our intervals. That means that it's increasing for x between 0 and minus 2 and x greater than 2. So what on earth happened there? Okay. What the heck? My PDF in the background's gone. Okay, that's very annoying. Well, let's go without. Increasing, decreasing, decreasing. Second order differential would be 12x squared minus 16. Let's find our inflection points, as I haven't got the question anymore. So 0 is equal to the double differential of this, which is equal to 12x squared minus 16. Well, obviously we can divide through by 4, we get 3x squared minus 4 is equal to 0, so therefore x would be equal to square root 2 over 3 plus or minus 2 solutions, so therefore we've got our number line here, minus square root 2 over 3, square root 2 over 3, and therefore in between these points, let's think about our second order differential. So our second order differential between these points, if we pick the point 0, we'd have less than 0, f double dash greater than 0, f double dash less than 0. Okay. No, less than 0, other way around. Less than 0, and so therefore intervals, this is obviously it's decreasing the whole way through here, so we can think about it being decreasing and increasing, increasing, decreasing. So concave, because it looks like a cave. Convex. I dislike it when people put concave down, concave up. Apologies that it said that on the question. Looks like I've got to go, but the sketch is going to look something like that.